Have you ever looked at the device in your hand or on your desk and wondered how it actually came to be? From just an idea to the physical thing you're using right now? Well, it's not some random flash of genius. It's a blueprint, a really methodical and surprisingly universal process that's behind almost every piece of technology we use. And today, we're going to pull back the curtain on that exact blueprint. This quote really nails the heart of engineering, doesn't it? This whole journey of creating hardware isn't a straight line. It's all about learning. Every single stage we're about to walk through is built on this one idea. You have to keep asking questions, finding answers, and learning something new every single day. And that's the real secret, isn't it? It's not about a eureka moment. Real hardware innovation is a structured journey. It starts with careful planning and, a whole lot of documents, long before anyone even thinks about touching a piece of silicon. Okay, so here is our game plan. We're going to follow 5 critical stages. We'll start with that initial spark of an idea, then see how it gets turned into a master plan. We'll watch it take physical form, see it survive a brutal round of testing, and finally, we'll see how a project is properly wrapped up for the future. So let's dive right in.
First up, the idea and the team. This is where it all begins. It's where you figure out what you're building, and just as important, who is going to build it. And trust me, if you get this part wrong, nothing else is going to matter.
So it all kicks off with this one document, the Product Feature Guideline, or PFG. It really just boils down to 3 brutally simple questions. 1, what is this thing supposed to do? 2, can we actually afford to make it? And 3, as the source puts it, you have to think it twice. Is it even worth the risk? Answering these questions honestly, right at the start, that can save you millions of dollars and years of headaches down the road. Okay, once you know the what, you need the who. And building hardware is a total team sport. It's not a one-person show. You need a huge range of specialists. Your electrical and mechanical engineers designing the physical thing, the software folks who breathe life into it, and of course, the QA and testing teams whose entire job is to try and break it. So, the idea is solid and the team is in place. Now we move into phase 2, drafting the master plan. This is where the big, exciting idea gets real, like spreadsheet real. Every feature gets turned into a line item, every goal gets a deadline, and everything gets a price tag. And this timeline shows you something really important. You don't just build the final thing once and call it a day. No way. You do it in stages. You start with just the circuit board. Then, in the next phase, you add the casing and mechanical parts. It's this constant cycle. Build, test, find what's broken, and make it better for the next round. A super critical document here is the bill of materials, the BOM. You can think of it as the project's master recipe and its shopping list, all rolled into one. Every single tiny resistor, every capacitor, every chip, it's all listed here. And if you get this wrong, forget one tiny component, you can bring a massive production line to a screeching halt. It's the financial backbone of the entire project. But the really smart teams take it a step further. They make what's called a functional BOM. So instead of just a giant, overwhelming list of parts, they group them by what they actually do. So why is this so cool? Well, it means you can look at your product and say, okay, the audio circuit costs exactly this much. If you suddenly need to cut costs, you know precisely the financial hit of changing or even removing a feature. It's incredibly powerful. The plan is locked in. The spreadsheets are done. Now it's time for the engineers to work their magic. In this next phase, we get to see how those digital blueprints are painstakingly turned into a physical thing you can actually hold. Now listen up, because this is a super important concept to get. The difference between a schematic and a layout. A schematic is the logical plan. It's the blueprint that says chip A connects to resistor B. It's the what. The layout, on the other hand, is the physical map. It decides the exact path on the circuit board that the little copper line takes to make that connection. It's the how. You can have a perfect schematic, a flawless plan, but a bad layout can make your product unstable and unreliable. Period. And I absolutely love this piece of advice from the source material. It just gets it. Great engineering isn't about making things complicated. It's about making them clear, elegant. A truly great schematic is one that another engineer can just look at and instantly get what you are trying to do. It really is an art form. And the layout is where that art meets some serious, painstaking science. We are talking about details you can't even see. The width of a tiny copper line, the space between 2 of them. Engineers even have to make sure 2 signals traveling on different paths arrive at their destination at the exact same picosecond. It's insane. Get it wrong by a fraction of a millimeter, and the whole thing could fail. So, the design is finally done. The first prototypes have been built and delivered. And now comes the moment of truth. Welcome to the gauntlet of testing, where all those beautiful plans and elegant designs slam right into the harsh reality of physics.
This is it. The one question that keeps engineers up at night. You can simulate everything, check every connection a dozen times, but you never really know until you hit that power switch for the very first time. Are you going to see a little green LED light up? Or are you going to see a puff of smoke?
That very first test is called board bring up, or BBU, and it's the most basic step. You're not trying to test fancy features yet. You are literally just checking for a pulse. Are the main power lines at the right voltage? Is the clock ticking? You're just asking one simple question. Is it alive? Everything else comes after that.
So once you know it's alive, you do what's called an electrical analysis, or EA. And this is like giving the board a full medical workup. The engineers break out the heavy-duty gear, oscilloscopes, logic analyzers, all of it. And they measure everything: signal quality, timing, noise. The result is this huge report that proves the design is electrically sound and becomes a permanent record for the project.
And you will find problems. That's a guarantee. The trick is how you handle them. Everything gets logged methodically in an issue tracker. So look at this. An overcurrent risk was found. It's assigned to the electrical engineering lead, its status is open, and the plan is to add a fuse in the next version. It's this super disciplined process of hunting, owning, and squashing every single bug. Okay, so after months and months of work, the product is stable, the big bugs are gone. You'd think you're done, right? Well, not quite. There is one last absolutely critical stage: making sure this project has a legacy. Because here's the thing: success isn't just shipping a product. It's making sure that 5 years from now, someone who's never even met the original team can come in, look at the files, and understand how to manufacture, support, or even improve that product. The project has to live on through its documentation. And this is what that legacy looks like. It's a complete package with the whole story: the final schematics, the files for the factory, every single test report, every failure analysis, all the assembly instructions. It is basically the project's entire brain, perfectly preserved for any future teams to learn from.
So we've just walked through this incredible, detailed blueprint for how to build a product right. But that leaves us with a much bigger question, doesn't it? This process ensures you build the thing correctly from an engineering standpoint. But how do you know you're building the right thing in the first place? You know, the thing customers actually want? And that's the bridge between a great engineering project and a truly great product. And maybe a topic for another day.